Okay, as the last speaker, final speaker of today, we have Quynh, who will tell us about computational advantage with polyloglog-depth noisy circuits. Let's take it away.
Yeah, thanks. Hello, everyone. Thanks for coming to my talk. So yeah, today I'm very happy to tell you about this joint work with Anshu, Yunxiao Liu, and Chris Pattison. And yeah, I'll talk about quantum computational advantage with polyloglog-depth noisy circuits. So this paper is essentially, that's something we're working on. It's essentially a quantum fault tolerance result. So for this talk, is the outline of the talk. So I'll start by giving some motivations for the model of quantum fault tolerance that we study in this work, which is called a fully quantum model. And then why we care about studying the depth overhead of this model. And then I'll state the results. And then I'll describe the the ideas in the two main results, which is a fully quantum fault tolerant scheme and its application for fault tolerant IQPE circuit sampling. And then I'll end with some open questions. So yeah, so some background. So as we all know, we need quantum fault tolerance to realize quantum computers. And the goal here is we want to transform an ideal circuit to a fault tolerant version such that the output distributions of these two circuits are close in the total variational distance, even when the components of C are subject to noise below some constant threshold. And we have to pay a price in doing this. So that's the fault tolerance overhead defined by the ratio between the sizes of the two circuits. And we can also be more fine-grained to define the space overhead or the width overhead, which is the ratio between the width of C bar and the width of C. And also we can define the time overhead, which is the ratio between the depths. So one of the most important results in quantum information is the quantum threshold theorem, proven in the 90s, that shows we can do fault tolerance with a polylog overhead in both space and time. So the motivations for our work are twofold. So on the theory side, so the current kind of status of the field of quantum fault tolerance is that most quantum fault tolerance schemes that we know of assume noiseless and quick classical computations. And this is a very practically motivated model. And yeah, so in this model, we're allowed to do mid-circuit measurements. We can do noiseless classical computation. We do post-selection, feedback, and like error correction, etc. So how about fully quantum fault tolerance? Like, what if we don't allow any of these options? So the only node scheme is the original threshold theorem, proven in Aaron Benor. And a motivation for studying this is, as quoted in Aaron Benor, where they said, we would like a quantum model that is complete in the sense that it can be made fault tolerant within itself. So then now in this model, we can ask how far we can push the overheads of doing fault tolerance in this model. So in this work, we care about depth overhead. And here, some related works did study depth overhead, but in this model that assumes a noiseless and classical computation. So in these works, the author kind of described how to do constant quantum depth overhead, but assuming polylog, noiseless classical computation. And yeah, so on the practical side, right now in most hardware, the mid-circuit measurements and classical feedback are often much slower and noisier than doing the unitary gates. And near-term devices might lack some of the main requirements for QEC. Like, for example, we might find it difficult right now to do mid-circuit to initialize fresh oscillators in the middle of computation. And so a question here on near-term devices is, can we demonstrate quantum computational advantage from shallow circuits? So in this area, we know that from this foundational work of DiVincenzo and Terhao, that exactly sampling from constant depth ideal circuit is classically hard. Of course, assuming a non-collapsive pH and etc. So here, like experimentalists have been trying to run this random circuit sampling on the current device and hoping to demonstrate quantum advantage. But recently, there have been like classical algorithms for simulating noisy random circuits. So it seems that the foundation for doing quantum advantage with shallow, noisy random circuits is kind of right now being not very clear if it gives us a quantum advantage. So then the question here is, can we get quantum advantage on noisy shallow circuits with minimal QEC capabilities? So in this work, we make progress in this question, and we show that we can do this with polylog-depth circuits. So more precisely, the main result that we prove in our work is a new fully quantum fault-tolerant scheme against the standard local stochastic noise model that I will not define, but it's you can just think of it as each gate failing independently with some constant probability. So I'll refer to the number of qubits in a circuit as W, standing for the width, and the depth as D. So we give a protocol that has polylog-depth overhead, polylog-space overhead, and the degree of the polylog here could be as low as 2 plus little 1. And yeah, these overheads hold for any circuits of any depth. Like if you give me any circuit of any kind of depth, and I'll give you a fault-tolerant version of it. Yeah, some simple modification of this can also give us a fully quantum fault-tolerant scheme with constant space overhead and polylog time overhead. So as mentioned, the only prior works that rigorously show a fully quantum fault-tolerant scheme is Arnaud-Benor that gives polylog-depth overhead. And interestingly, in this paper, they conjecture that polylog-depth overhead is possible. And in 2004, there's this PhD thesis by Anne from Caltech, where she kind of claimed to prove this conjecture using a very different method from ours, but the proof is quite incomplete.
So the constant space overhead and polylog time, was that part known before?
This is known for the model that assumes noiseless classical computation.
So this is also new in the fully quantum setting.
Sorry, this is, I think this is the first time that you can do this with fully quantum.
Yeah.
That's right. Yeah. So it wasn't known. Yeah, thank you.
And what about the constants? Like, is this you're going to talk about it?
It's the constant is huge. We use quantum LTC. So essentially, this came from the same ideas from Chris's talk an hour ago. Yeah.
This is a really dumb question, but just so that I'm on the right page, this is multiplicative overhead, right?
Yeah.
Okay, cool.
Yeah, that's right.
Cool.
Yeah.
And by the way, when you say fully quantum, sort of what are the assumptions of the model? Like, can I effectively simulate noiseless classical computation within a quantum computer? Right. I mean, like I'm confused, like, because if there's also this result by Haranov, right? Like, if I have a fully closed quantum system, error will overtake everything.
Oh yeah. So the model here is you can do noisy unitary gates, and yes, you have to be able to do mid-circuit noisy initializations.
Oh, yeah. I see.
Yeah, so that's what I meant.
Mid-circuit noisy initializations.
Yes.
You have access to clean qubits.
No, you have access to noisy qubits, mid circuits.
Hmm.
Yeah, that's a requirement if you want to run a circuit that is longer than log depth, right? As Scott mentioned.
I see. So and that's the only non-unitary resource
Yeah.
that you have.
This is not geometric local. This is
No.
well,
Yeah, this is also all.
Got it.
So yeah, so the title of this talk is an application of this result. So we apply this on the ensemble of IQP circuits that I'll define later in the talk. So that establishes an ensemble of noisy quantum circuits without classical computation, mid-circuit measurements, and without mid-circuit fresh oscillators. And the idea here is you apply this theorem, the fault tolerance result, and then because the depth is so low, you can essentially get rid of the need for mid-circuit fresh oscillators. So that gives us a family of quantum circuit that has polyloglog-depth and this many qubits, and under reasonable complexity-theoretic assumptions, no polynomial time classical algorithm can sample from this circuit. Okay. So some prior works in this line of in this area. So that's a paper by Paletta et al. From 2023, where they show that they gave a fault tolerant implementation of IQP circuit, but there they did have to assume a layer of polylog-depth, noiseless classical computation and feed forward. And that's also another paper by Tiago, Yun Chao, and Anthony that study fault-tolerant IQP circuits against a special noise model where you only have noise in the input. Okay, so in the rest of this talk, I'll divide into two parts. So first, I'll describe the fault-tolerant scheme. So here's a sketch. So as mentioned, this is based on the scheme of in a previous work of myself and Chris. And here we used quantum LTC, and we were able to achieve constant space and nearly log time overhead, assuming an amount of polyloglog-depth noiseless classical computation. And our starting point here is that a simple modification of this paper gives us a polylog-log quantum depth overhead scheme, assuming noiseless polylog-depth classical. So then the second step is we use classical fault tolerance by von Neumann and Pippinger to get rid of this noiseless classical computation. So there are a few key points why this works. So the first point is that it turns out that in the classical case, we can do fault tolerance in constant depth overhead. And the second point is that the quantum LTC here we used in this construction has a constant time decoder, which I'll define what that means later. So then combining these two, and yeah, there's some other challenge when in incorporating classical fault tolerance in quantum fault tolerance, but combining these, we can get the main result. Okay, so now let me quickly recap the fault tolerance scheme in this paper that you saw in Chris's talk. So the main object here is we have a quantum LTC code block. So we'll encode the logical qubits in the quantum code in a kind of logarithmic side code block. And yeah, for simplicity, let me assume that we have an asymptotically good quantum LTC. And this, as you also saw in Chris's talk, this can be dropped by a concatenation trick. But yeah, let's just assume we have a good QLTC. So So yeah, the main idea of this, the main structure of this protocol is we have a single shot efficient decoder. We know how to do transversal gates like CNOT and poly. And then to do the Clifford gates and non-Clifford gates, we do gate teleportation. Yeah, so yeah, we prepare these resource states and inject it into the circuit. So the first property that we need is a constant time decoder for the QLTC. So this was shown in my paper with Chris. So this was shown on this family of almost good QLTC by Dinur, Lin, and Vidic, and using some result of Kalachev and Pantelev. So we show that given the syndrome of the code, then we can run a constant depth circuit to find a proposed poly correction on the to apply on the code, such that the residual error is suppressed by a constant factor. So if the input error has weight E, then we're guaranteed that by running this is just in constant time, we can suppress the error by some factor, in addition to some like extra error coming from the measurement errors. And this constant time decoder suffices for us to maintain the computation maintain the code block throughout the entire computation. Yeah, and yeah, this statement is for almost good QLTC, and yeah, we can make the rest of the talk work for almost good QLTC, but again, I'll assume we have good QLTC and a constant time decoder like this. Okay, so the first idea to improve the time overhead in this work is to, so in this like log side quantum LTC code block, we're just gonna use one logical qubit instead of using all the logical qubits in it. So now each logical qubit in the ideal circuit is encoded in a good quantum LTC code block of log size like this. And yeah, it turns out that the gate serialization time overhead that Chris showed in his talk, that overhead is gone after we do this. After we set the number of logical qubits per block as 1. So this immediately gives us a polylog-log quantum depth overhead. So yeah. So yeah, constant time decoder gives us a way to do the identity gate without any classical computation. And yeah, we also have transversal gates that doesn't require classical computation. So now we're left with the task is to remove all the classical computation in the other parts of this fault tolerance scheme. So it turns out that classical computation are used kind of everywhere in the rest of this construction. So for example, when you do gate teleportation, you need to figure out whether or not to do a Poly or Clifford fix-up, and that usually requires a classical computation and feed forward. Yeah.
For the constant time decoder, you said there's no classical computation, so you just run it.
That's right. Yeah. So yeah, we can kind of divide these classical adaptivity requirements into 2 types. So the first type that I like to think of is Poly and Clifford fix-ups. So some example of this is, for example, when we do like stabilizer code encoding by doing stabilizer measurements, we need to compute and apply a poly correction to shift the state back to the code space. So that's where we need a poly fix-up. So similarly, in error correction, we need to compute the poly correction from syndromes. Yeah, and as I mentioned, in gate teleportation, we need to determine whether or not to apply the Clifford or Pauli fixer. So type 2 of classical adaptivity is post-selection and routing. So examples include, for example, in magic state distillation, based on error detection. If here, what people do is that if we detect less than 2 errors, then we accept the state and move to the next round of magic state distillation, else we discard. And this involves a classical computation. Other examples include preparing verified cat state, like in Shor's error correction. And in our case, we have this kind of cute example of doing QLTC verification test. And here the goal is to proceed with a state if and only if the state is sufficiently close to the code space. And yeah, and that requires some kind of threshold computation on the syndrome measurement outcomes. Okay, so the way we remove these classical computations is via classical fault tolerance. So we're going to use this kind of classical fault tolerance scheme by von Neumann and Pippinger based on repetition code. So the idea here is each bit in the classical computation is encoded in a logarithmic size repetition code. And here you can think of it as the size of the computation that we want to run, and epsilon is a target error. So this scheme goes something like this. So yeah, each bit is encoded in a repetition code. So a repetition code has transversal topology, and that's universal for classical computation. So we just interleave between transversal topology and an error correction circuit. And this one can show that this error correction can be done in constant depth by kind of doing some majority vote on an expander within each repetition code block. So to apply this scheme on the auxiliary computations in quantum fault tolerance, this little n here, the size here is kind of like polylog W. As a reminder, W is like the number of qubits in the quantum circuit that we want to run. But the interesting thing is the target error here, we need it to be like inverse in the size of the global quantum computation that we need to run. So it's like 1 over WD. So this code block is like logarithmic in the size of the global quantum computation that we want to run. But the key point is classical fault tolerance has constant time overhead. So that's fine for us. Yeah, so as an example, we run this on when we want to determine whether or not to apply a logical Clifford fix-up when we do magic gate teleportation. But there's a challenge in applying this protocol, at least naively. The subtlety here is that in this fault tolerance protocol, we kind of assumes that the input is already encoded in a repetition code, which is not the case within the context of quantum fault tolerance. So here, the input that we're given is kind of a bare bit string. Like the input here could be like a list of syndrome measurement outcomes. And so somehow we need to kind of encode this input into a repetition code. Right, so this is how we do it. So the key observation here is that the auxiliary classical computations in quantum fault tolerance are inherently tolerant against input noise. And this is just by design of doing quantum fault tolerance. So then all we need to do is to figure out a way to fault tolerantly encode each bit to a repetition code such that the logical error rate of the repetition code is proportional to the physical error rate up to some constant factors. And it turns out that this is doable. for example, in this PhD thesis, An did this by using 2D Toomes rule. So we give a similar lemma for this fault-tolerant encoding using kind of just majority vote on expanders. Okay, so together, this fault-tolerant like repetition code encoding and the classical fault-tolerant scheme allows us to get rid of the assumption of noiseless classical computation. And so to apply this to quantum fault tolerance, so let's see an example. Okay, so here we have magic gate teleportation. Let's say we want to teleport a T gate. So this circuit is a T gate teleportation, and it is being run at the logical level of the underlying quantum LTC code. So what we'll do here is we'll do the fault tolerant fan out and run the fault tolerant classical computation in this, like on the measurement outcomes of this like transversal measurement. And then while doing this classical computation, we'll apply the constant depth like decoder of the QLTC to maintain this code state. So after getting the repetition code encoding of the output of this classical computation, we'll do a kind of a trick to apply to control on this repetition code to apply the logical Clifford correction by doing some sort of like transversal control swap gates, physical control swap gates. Yeah, similarly for the like type 2 classical adaptivity, we can also do the same thing to compute the decision of accepting or rejecting a state. And then for the routing part, we can also just perform a sorting networks conditioned on the repetition code outcome of the classical computation. Yeah, so that's a kind of an overview of this polylog-depth fully quantum fault tolerance. So now I'll tell you about the application for IQP sampling. So IQP sampling was proposed to demonstrate quantum advantage. So the model here is we have a layer of Hadamard gates. We perform a sequence of diagonal gates, and then we do Hadamard gate and then measurements. So the following works have shown that assuming the non-collapsive pH and a reasonable average case assumption on the average case hardness of approximating some family of partition functions, there exists a family of constant depth IQP circuits, so that the diagonal part is composed of the T and CZ gates, such that no polynomial time classical algorithm can sample from the circuit. So yeah, we can just directly apply our scheme to this circuit, this constant depth IQP circuit, and we get polylog-depth overhead. We have this space. N times polylog n many physical qubits, and this fault-tolerant circuit uses noisy mid-circuit initializations of 0 states. So finally, what we do to remove this mid-circuit initializations is to kind of use some lemma from this paper, and essentially the idea is that we can simulate a qubit initialization at depth d by initializing 3 to the d many qubits at the first time step of the computation. So d here in our case is polylog-log. So that is crucial to obtain a overall polynomial sized fault tolerant quantum circuit, IQP circuit. And And yeah, and that circuit falls into the complexity class called NISC, defined by the following authors. So in other words, this result shows that this NISC circuits are classically hard to sample from under these complexity theoretic assumptions. Oh yeah.
I'm wondering about the different overheads you're giving.
Mhm.
Is it crucial that they are at noiseless, or is it conceivable that you could have a scheme with higher overhead? Like what breaks if you have higher overhead at depth,
Right. So you mean the depth overhead here?
for example? Yeah.
Yeah. So so previously with the Aharonov-Menor scheme, this would be polylog,
Okay.
and so you would not be able to remove this mid-circuit initializations with a because the overhead of this like lemma is like exponential in the depths. Yeah. Yeah.
Another one is, so what's like the total variation distance that you get here? You know, previously the hardness is like 1 over poly error. So
yeah, this is we can also get 1 over poly
like
TVD.
any 1 over poly, or do you even get exponential error suppression? Or
We cannot get exponential suppression.
so just
Yeah, because like this polylog-log, there's a epsilon hidden here. So if you want to get a TVD of epsilon TVD distance, this will be polylog-log n over epsilon. So you can't do. Yeah. So yeah, like if you're okay with having mid-circuit initializations, then you can. Yeah, exponentially small epsilon would lead to polylog-depth, but then removing mid-circuit initializations will incur a superpolynomial space overhead.
In low
yeah,
dimensions,
Yeah.
I guess in low dimension you get polylog-depth. Is it possible to embed the thing into low dimensions?
To low dimensions.
Like 2 dimensions?
We use a QRTC, so probably no. But maybe like Chris has some work that show how to kind of simulate like non-local LDPC code in 2D by concatenating with surface code. So maybe that could achieve that, the thing that you're asking for. But yeah, I don't see immediately how to get low dimensions like this. Yeah, and I guess the depth overhead, the classical fault tolerance scheme that get constant depth overhead also had to assume all-to-all connectivity. Yeah. Yeah. Okay. Yeah. So actually, that's all I have for today. So here's some future directions. So is constant depth overhead quantum fault tolerance possible in this model? It seems very unclear to me, and yeah. So if I tend to believe that this is not possible. So if not, then are there interesting families of circuits for which constant depth overhead is possible? Well, for this, we know of this. We know how to do this for Clifford circuits from this paper by Bravi, Goetzet, Quynh, and Thomas Michael. And then the final open question I have here is: can we get super polynomial quantum advantage from constant depth noisy circuits? That's all I have. Thank you.
Okay. Any more questions for Quynh?
So I guess this is a really impractical scheme.
Yeah.
Do you have any, I guess, thoughts on like what the most practical variant of the scheme would be, which maybe doesn't like quite get you there?
I hope that maybe the QLTC can be replaced by maybe 40 toroid code or something. to get a smaller constant. Yeah, I guess even the classical fault tolerance scheme that we're using here has pretty big constants. So
Is there like a single bottleneck where it's like species suboptimal?
like in the practical sense,
I guess, yeah.
the main bottleneck here is the QRTC. Yeah. And then the classical fault tolerance, that like constants in that sense. Yeah, I think.
Any more? Yeah.
And so why is this constant depth unitary circuit question so intriguing? Like, why are you not happy with the polyloglog-depth?
Yeah, that's a good question. It seems to me that if you can prove this, it seems you would need a very different technique from
I see.
what we do here.
So it's
I think
interesting from techniques perspective.
yeah.
Okay. Any more questions? Okay, if not, then let's thank Quynh again. Yeah, and that's it for today. Thank you very much.